All right, so we're going to talk about these things called binomial distributions or binomial random variables. All right, so they come about when a specific sort of setting occurs with just a random variable. So again, it's a subset of random variables. Um, and so we have this kind of acronym that we use. So the important stuff to get down is probably what's in the green box. So a binomial setting arises when we perform several independent trials of the same chance process and record the number of times that a particular outcome occurs. And the four conditions for a binomial setting are, the first one is be binary. So you want it to be such that for your outcomes, you can either determine an outcome as a success or a failure. So you're able to classify the outcomes as success or failure. I stands for independent. Trials must be independent, meaning knowing the result of one does not influence the result of a future trial. N stands for number, and that just means the fixed number, number of trials N, of the process is fixed. There are a finite number of trials, and it's fixed in advance. And then S stands for success, and that means there's the same probability of success on each trial. And that's kind of tied to the independent one. So knowing that one trial was a success doesn't change the probability that another trial will be a success. And so the acronym we use to remember this is BINS. Binary, independent, number, and success. So we'll start out with just some baby steps. Before we do that. So if you have a binomial random variable, the probability distribution of that binomial random variable is a binomial distribution. And so this is important to write down. The parameters that describe the binomial distribution are n and p. And so the shorthand for that is bn comma p. So a lot like if we know a distribution is normal, we'll write it out as n comma the mean comma the standard deviation. And the mean and standard deviation literally tell you the only two things you would need to know technically to be able to graph that particular normal distribution, right? Same thing with a binomial distribution, it's just the parameters are different. The parameters we need to know are n, the number of trials, remember that's fixed, and p, the probability of success. And same idea, as long as we know those two things, our calculator is going to have a function that can calculate that binomial distribution for us. So now we'll take some baby steps into an example. First thing we're going to do is just try to identify if the setting is binomial or not. So I'm going to give you 3 settings, and we're going to check to see if it's binomial or if it's not, if it's just a random variable. All right, roll a fair die 10 times and let x be the number of 6s. All right, so is it binary? And the answer here is yes. Since we're only concerned about 6s, we would consider a 6 is a success. And then anything else, we would call a failure in that setting, right? So that can be considered binary. Independent. Are dice rolls independent? Does the dice remember what it rolled before? The dice does not remember what it rolled before, so one outcome will not affect the next. So yes, these are independent. N, is there a fixed number of trials? In this case, yeah. We want to roll it 10 times, right? So we'll say lowercase n equals 10. Check. Is there a fixed number of trials? And then S, is the probability of success the same for every roll? Yeah, so the probability of success in this case would be the probability that we roll a 6 on a fair 6-sided die. That would just be 1 out of 6, right? Whoops, I want S, 1 out of 6. That means the probability of failure is 5 out of 6. So yes, this is a binomial random variable. So B for binomial, and then I said the parameters would be fixed number of trials, 10, comma, probability of success, 1/6. All right, let's look at B. Shoot a basketball 20 times from various distance on the court, and we'll let y equal the number of shots made. All right, is it binary? Sure. Right, we would consider success. I guess I'll use the same. A make is a success, and a miss is a failure. Independent? I'm going to say maybe. It's a little iffy. There's a lot of evidence that you can get streaks going, you can build your confidence up, and then a previous shot being made could affect the outcome of a next shot. But let's say we had a robot doing it. Then sure, the outcomes are independent. Fixed number of trials? Yes. Check. N equals 20, right? And last, the fixed probability of success. That's a big no, because we're moving various distances on the court, right? That probability of success is going to be different depending on how close or far away you are from the basket. So the probability of making it is not the same for every shot, so no. I'll say P is different from different positions. All right, so I'm just going to say not binomial. Yeah, so this one's actually not binomial. It fails the first condition. There's no way to project success or failure since they just said let C equal color. If they said like let C equal blue, then we could call success being a blue car. Anything else is a failure. But no, everything is going to be a color of car. So immediately it fails the binary parameter, and it is not binomial. Great. So next time we'll do a couple of, we'll finish up these notes, and then we'll also finish up 6.3 part 2, which is much shorter. And I'll show you some new functions, the binomial function on your calculator that can help you compute some of these probabilities once you have verified that you are in fact in a binomial setting. But we will stop